Welcome to Monday. Today is March 23rd. Yes, my birthday was yesterday. And today is actually Mark's birthday, my husband. So we share one birthday cake. Anyway, okay, so March 23rd is Monday. We have a new topic. And this is actually my favorite topic in all of organic chemistry. It's Enols and Enolates. We'll spend a couple weeks on these on this chapter. This is chapter 22 in your book. You do have the slides available for you on Canvas. And when I was preparing for this, I was looking at some of those slides. I will give you your additional activities this week, additional questions in your POGL book. So we have basically POGL 22A, B, and C. I think that's right. I think it's 22. I'm actually going to go to campus tomorrow and try to get my POGL book. So I'll have a better tomorrow. I'm recording this on Friday. Yeah, I'm recording on Friday. So anyway, so this week I'll have the POGL book. But anyway, okay, that's enough about that. Let's just go ahead and start into this chapter. And what I want to do is tell you what we're going to focus on today for about 20-25 minutes. And we're going to talk, an enol is something like this. So that would be an enol. And an enolate would be something like this. Okay, so this is an enolate. So just what is the difference between an enol and an enolate? Well, one has no charge, the enol, and remember the donkey enol? What's the donkey say? And the enolate has a charge, okay? And usually this negative charge is has a counter ion like a positive sodium or lithium, okay? So that's usually because this is generated maybe using sodium hydroxide. You're also going to see sodium ethoxide, maybe sodium methoxide, and you're also going to see LDA. So what is LDA? That is lithium. And then this is diisobutyl amide. Okay. And so how is that even made? You basically take diisobutyl amine and you react it with N-butyl lithium. And this does an acid-base chemistry. This is actually your base, and this is your acid here, and it will deprotonate. This is your acid. What's the pKa? Remember we said amines are about 36. And then the nitrogen gets deprotonated. See, 1, 2, 3, 4. 1, 2, 3, 4. Okay, so it gets deprotonated, and then this carbon picks up this hydrogen to make butane. So that's your conjugate acid, which is an alkane, pKa of 50. This is your conjugate base. So we're comparing 50 with 36. So which way does the electron flow arrow go? Towards the 50. Okay, so this is how you make LDA. Now, your reagents in this chapter, you're going to have a good amount of reactions. You're going to get some reaction sheets, okay? Your reagents are going to be all about that base. No trouble. Is that the Meghan Trainor song? Okay. So I got to teach you some acid-base chemistry, and we're going to talk about pKa's and write some acid-base chemistry. So these are bases: sodium hydroxide, sodium ethoxide, LDA, you might see sodium methoxide. Those are pretty much your reagents. So you wouldn't think this chapter would be challenging, but you'll see. I'm going to give you some tricks, right? I'm going to give you some tips. But those are the bases that you're going to typically use. And I expect you to know when to use which one. Okay, so when you do Aldol, we always use this for the Aldol, sodium hydroxide. Whenever we do Clazian, we're going to use the sodium alkoxides. And whenever we do alpha substitution reactions, we're going to use LDA. Okay, so what's an alpha substitution reaction? Well, alpha substitution. That is the mechanism, by the way. You're going to have to know the mechanism. This is your new mechanism. So if you take like this ketone here, okay, you all know that that's cyclohexanone. And you know it's a ketone. Now, if you react this with sodium hydroxide, now I'm going to give you some new information that you might not be aware of. And this is slide, and I would print it off if I were you, slide number 59 of the 76 slides, okay? And you'll see the pKa values there. And some of the pKa values, acetone, pKa value 20. Now, let's think about that. pKa value of an alkane, sp3, carbon, hydrogen, 50, right? What about an alkyne? A terminal alkyne, sp, carbon, hydrogen, 25. You also, so here's 20. So is this more or less acidic? Which proton are we talking about? We're talking about the alpha. Okay, so we're talking about this hydrogen here. So the alpha carbon. The alpha carbon of a ketone has a pKa of 20. Now why is that? Well, when you have a base and it abstracts that hydrogen, what is the conjugate base? It's resonance stabilized. See? So there's so it's actually, we could draw this one down here. So electrons go there. So you have two resonance structures. I call that my monkey face. You all see that? The lone pairs. And then the negative charge, I call that monkey face. Okay, so I might tell you to draw your monkey face. Okay, and you see how that's on that alpha carbon. So that alpha carbon now is a nucleophile. Remember, that's a powerful thing. The nucleophiles, carbon nucleophiles, you name them. What are they? Remember, we started the chapter with the Grignards. Remember the Oompalong? We have the organolithiums, all right? We also had the alkyne. We treat that with base, you can get a negative carbon. We also have sodium nitrile. You've all been using that. It's a negative carbon. Hello, folks. We have a negative carbon here, and it's called, in this case, if you reacted this with like sodium hydroxide, the sodium would hang out here by the negative charge, and that would be an enolate. And those are the intermediates of the alpha substitution mechanism. And then that's your nucleophile. So we're going to do some reactions with that, but I need you to really understand your bases. And to finish up page 59, we have some more. That reaction, and that we have some more pKa values I want you to know. Let's do, so we have the ketone. So pKa is 20. All right, and so that resonance structure, this is the conjugate. Okay, it's your conjugate base, pK of 20. That's a ketone. This is an ester. Where's your alpha carbon? That's what you're looking for. This is the oxygen. That is not an alpha carbon. Your alpha carbon is right here. Okay, so there's 3 hydrogens there. So what does that conjugate base look like? Monkey face. All right, and if we have to draw our resonance structures, all right, and what's that pKa? That one is 24, so it's up there with the alkynes. So a ketone is more acidic than an ester. That's going to be important. You're going to need to know that. Then we have 3 more that I need you to know. Okay, so we have this, and this is a beta keto ketone. Okay, beta keto ketone. You like that? So this is your alpha, and this is your beta. All right, so we do have an alpha here, we have an alpha here, and we have an alpha here. Okay, those are the carbons right next door to a carbonyl. So, which one's your most acidic? You're going to have to do that sometimes. It will be this one, okay? This pKa here, the cost, taking that one is a 9, okay? So why is that? Well, let's take a base, abstract that hydrogen. And I'm going to just redraw it. You just want to redraw it just like you did. But now, there's your negative on that carbon. See my monkey face? If you had to draw your resonance structures, they would look something like this. Okay, so there's one. You go the other way. So how many resonance structures is that? 3. 3 resonance structures. 3 resonance structures is why the pKa is lower, a 9. All right, and then we have, so that's a beta ketone, a beta keto ketone. And then we have 2 more. What about a beta keto ester? Where's our alpha? That would be an alpha carbon. That would be an alpha carbon. This is not an alpha carbon, folks. That's an oxygen. Okay, so we have hydrogens here, and we have hydrogens here. Which one's the most acidic? It would be this one here, this alpha, and the pKa of that is 11. So let me just draw. See how I just redraw this? This is your easiest bet. Put your monkey face right there, okay? And if I have to draw the resonance structures, then this is how you do it. I'm sure you're going to have to do that in your POGL for this week. Okay, and then you could draw it the other way. So you do get 3 resonance structures on these. pK is 11. Once again, the 9 is like 100 times more acidic, okay? So a 9 is more acidic than the 11. So that means a beta keto ketone is more acidic than a beta keto ester. Once again, you saw that earlier with the ketone. And then the other one we have, how about a beta keto ester? Diester, Okay, so this is a diester. That pKa is 13. Okay, so you add another. This has one ester. This has two esters. And now this is 100 times less acidic. So what's the cost of an ester? About 100. Okay, twofold. So those are your acidic protons. I told you I need you to write acid-base chemistry reactions. So let's look at cyclohexanone like we were going to earlier. Hopefully we'll have time for one reaction here. Sodium hydroxide. So this is a base. Now this is your acid. It's a ketone. You find your alpha carbon. Draw in your alpha hydrogen, okay? So I'm giving you your steps. 1, locate alpha carbon. Draw in your alpha hydrogen. 3, deprotonate to make your enolate. You're going to be doing this over and over in this chapter, okay? So what does that enolate look like? You just redraw your ketone. So redraw your structure and then add your monkey face. Okay? That's how you draw your enolate. So here's your monkey face. Okay, there's your monkey face. Now you can draw your resonance structures. Okay? That's your resonance structures. And this OH picked up this hydrogen, so that makes water. And once again, we're doing acid-base chemistry. So we do our acid, base, this is your conjugate base, and this is your conjugate acid. We assign pKa values to the acid. This one, it's a ketone. What did we say? pKa of 20, and then the water's pKa of about 15.7, which is 16. So your equilibrium arrow is going to point to the cyclohexanone by 4 zeros. It's about 10,000 times. Now, we call something quantitative. What can give us a quantitative deprotonation? Okay, and you're going to see those in your problems that are 99%. So what if we did this reaction with LDA? Remember I told you, if you do like, I told you got this base and then you got the sodium alkoxide base. So let's say sodium ethoxide. Well then what is your pKa? 16. So that's going to be about the same as water. Okay, so sodium hydroxide is going to be the same as sodium ethoxide. I will tell you when to use which one. Okay, remember I told you you're going to use the sodium hydroxide for the Aldol reaction, and I hope to do the Aldol reaction. And I told you you're going to use the sodium ethoxide for the Claisian. Okay, that's when you have an ester. Now, and then the other base we said was LDA. So when we're drawing mechanisms, by now, I want you to draw it out, and I want to see those lone pairs, okay? So that's LDA. Now we find, number 1, locate alpha carbon. There's your alpha carbon. Draw in the alpha hydrogens. Deprotonate, okay? To make, now the enolate. I want to make my enolate. So this says, redraw the structure. I redrew the structure, add my monkey face. There it is, okay? I want to draw the resonance structures. And that's my enolate. And this would be a lithium enolate. And then we have the nitrogen here, the LDA. And I've hit my 20 minutes. And it took away this hydrogen here. Okay? So this here is your acid, pKa 20, and this is your base. Over here, this is your conjugate base, the enolate, and then your protonated amine, the amine, becomes your conjugate acid. What's the pKa? 35. 35 or 36. So between 20 and 35. Yes, it's going all the way to the product. 35 minus 20 is about, what, 15? Okay, times towards your product. So we would call that quantitative deprotonation greater than or equal to 99%. And so your strongest base in this chapter is LDA. And when you're doing an alpha substitution reaction, many times you're going to want that LDA. But like I said, I'm going to teach you when to use what. Okay, so one of the goals you need to be able to do is understand and assign acidic protons. And it helps to know the pK values. So start looking at that. The other thing you need to do for this chapter is go ahead and learn how to write those acid-base reactions. You know I'm going to ask for it. And the other thing I want you, so you can go ahead and work on your problems for assigning the acidic protons. I'm going to teach you one other thing. I want to do, might take an extra 5 minutes. I want to teach you Aldol condensation reaction, because I want you to add that to your reaction sheet. And then I want you also to do crossed aldol condensation. And then tomorrow I will do the Claisian. So let's do this reaction. You would get something like this. We're going to do 2 reactions. And aldol, you want to use sodium hydroxide. Okay? So because it's cheap and easy, sodium hydroxide. Where's your alpha carbon? There it is, okay? The hydrogen here this is not acidic. That's an aldehyde, not acidic. So here we have our alpha, and then we want to draw in our hydrogens. So you locate alpha carbon, draw in hydrogens, and then deprotonate to make your monkey face. Okay, we're going to make monkey face. We're going to make our enolate. Because you have to know this mechanism. All right, so when we draw that, just draw the same. You draw the enolate, redraw, and then add monkey face to alpha carbon. There you go. See, there's your lone pair. Makes a negative charge. Now, what you want to draw for the aldol is it reacts with itself. Okay? It's called a condensation because 2 molecules come together to form one. All right? Now, okay. So they're going to come together to form one, and so you want to redraw the other one. So you're going to redraw this. Okay. So the first one is our nucleophile, and the second one is our electrophile. And so what happens is the nucleophile electrons will attack the electrophile, and you get the condensation. So what you want to do is you want to just redraw your nucleophile just the same way. So when you're forming product, hold on for just a second. Mark, let me call you back. I'm making a recording right now.
Oh, sorry, baby.
I'll call you right back. That's real life interruption there. Okay, so when you're forming I hate stopping it and redoing it. It kind of doesn't do so well. That's why I do that. All right, we're going to get this done in another minute. Okay, so I'm just going to do the one. So when you want to draw your products, I like to first, because it kind of gets confusing, redraw your nucleophile. Same. Okay, so we just did that. Now you're going to draw a new bond between this carbon and the carbonyl. Okay, and so count carbons. You can number them 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And then this is going to come up here just like this. So it's going to be your intermediate. All right, and you know you have to draw the intermediate. And then that's going to get protonated in water to regenerate your hydroxide, right? And so then you get this. One, 2, 3, 4, 5. Okay, this is called a beta hydroxy aldehyde. It could be a ketone, so it's kind of a beta hydroxy ketone, or it could be an aldehyde. Okay, but the whole point is this is your alpha, there's your carbonyl, and this is your beta. So a beta hydroxy carbonyl. Now, I always want to see this, but then you add heat, okay, and you're in sodium hydroxide, so it will lose water. And what happens then is you get 1, 2, 3, 4. You actually get an alpha beta unsaturated ketone. And I'll show you how to do that. And the reason why you do that is because this hydrogen, the alpha hydrogen, is more acidic than the original. Okay, and you're in sodium hydroxide. And so this will actually come here and deprotonate it. And this mechanism is a E1CB, which we'll talk about that next week. Next week, I mean tomorrow. Okay, but in the meantime, see if you can do a crossed aldol. So I'm going to go ahead and give you one problem. I'm going to give you one problem that I want you to try. You can add this to your Pogel points, okay? So I'm going to look for it, but this is called a crossed aldol condensation. And I want to see if you can do it. These are the two. Okay. Plus this molecule here. Okay. And you're going to put this in sodium hydroxide. And so I want to see your beta hydroxy ketone product. You can get this to your reaction sheet. And then I want you to add heat. And we'll talk about that tomorrow too. And then I'll give you your alpha beta unsaturated, well, it could be ketone or it could be aldehyde. Just say carbonyl product. Alpha beta unsaturated carbonyl product. So you'll get two products, show before and after. Okay.